welcome back everyone to this explainer. Today, we're doing something really exciting. We are bridging the massive gap between those perfect textbook circuits we all love to design and the messy physical reality of actual silicon. We're going to dive deep into parasitic extraction, or PEX. We'll give you the knowledge, the real-world layout techniques, and the exact interview answers you need to absolutely master this critical phase of chip design. Let's get into it. Here is our roadmap for today. We'll start with ideal schematics versus messy reality, move right into unmasking resistance and capacitance, walk through the PEX verification flow, dig into some crucial analog layout techniques, and finally break down DRC, LVS, and PEX so you know exactly how they compare.
All right, kicking things off with Section 1, Ideal Schematics versus Messy Reality. To really grasp what happens to our circuits when they go to layout, just imagine you're trying to send water from tank A to tank B. In your schematic, well, you assume you've got this super short, incredibly wide, perfectly frictionless pipe. The water just instantly teleports to the destination. But the actual physical layout, that's like building a real road or a real pipe between two actual cities. Suddenly your pipe is way too long, it's narrow, it's full of friction, herbs, and leaks. In VLSI, our electrical wires behave exactly like this. Drawing a long, narrow metal wire physically introduces friction. That's our resistance. And wires running right past each other, they act like unwanted storage tanks, adding capacitance. So the physical layout literally alters the electrical truth of your circuit. And look, in deep submicron nodes, these leaks and friction aren't just minor annoyances. They dictate whether your chip screams along at 5 gigahertz or completely melts down at 2.
And that brings us right to PEX, or parasitic extraction. Think of PEX as your diagnostic process. It measures all of those messy, real-world layout effects and converts them into unwanted electrical components. It tells us exactly how much unwanted resistance, capacitance, and sometimes inductance we've secretly tacked onto our circuit just by physically drawing it. Now, while R and C are going to dominate most of your designs, keep in mind that at ultra-high RF frequencies, PEX also has to extract inductance. That's where your nice straight wire suddenly decides to act like a tiny, totally unwanted magnetic coil.
Moving right along to Section 2, Unmasking Resistance and Capacitance.
Okay, so when we talk about parasitic resistance, we are looking straight at the friction in our electrical pipes. Every single time you draw a longer wire, you are actively cranking up that parasitic resistance. Remember, resistance is length divided by cross-sectional area, so longer equals more resistance, wider equals less. But hey, it's not just the metal traces. A huge, often hidden culprit here is via resistance. When you drop down from metal 4 to metal 1, you aren't just making a simple connection. You're actually forcing current through a super narrow, highly resistive tungsten plug. This is exactly why experienced layout engineers will drop via arrays, basically a grid of multiple vias, instead of just relying on a single one. It cuts that resistance down in parallel. And you're going to see this exact same effect with poly, diffusion, and contact resistance all over your layout.
On the flip side, we have to deal with capacitance. These are our unwanted energy storage tanks, and there are two main types you really need to look out for. First up is ground or substrate capacitance. This happens basically any time a metal wire runs over the substrate. The second is coupling capacitance, which flares up when two wires are routed right next to each other, interacting through their electric fields. Now, coupling capacitance is a massive headache, especially in sensitive circuits. Picture this, a noisy digital clock line running parallel to a delicate analog bias voltage. That coupling capacitance will literally inject high-frequency noise right into your clean analog signal. It completely destroys your signal-to-noise ratio.
And the mathematical impact of these physical realities, it is severe. Just look at the classic delay formula, roughly 0.69 times resistance times capacitance. Any extra R or C that gets extracted from your layout directly cranks up the delay of your signals. Your output node suddenly has this invisible, heavy load that the driver now has to fight to charge and discharge. Because of this exact math, a quote-unquote perfect circuit that passed your schematic simulation with flying colors can absolutely fail timing or performance requirements once it hits actual silicon.
All right, let's look at how we actually do this in Section 3, the PEX verification flow.
The PEX flow is a very clear, step-by-step chronological process. The extraction tool doesn't just eyeball your shapes and guess. First, it takes your layout database, like your GDS or Virtuoso file. But crucially, it combines that with highly specific technology information. See, the tool can't just look at a flat 2D shape and guess its capacitance. It needs the tech info to know the exact 3D vertical thickness of the metals and the precise dielectric constant of the insulator used in that specific fab.
It feeds all of this into the PEX tool, which crunches the geometry and spits out a shiny new extracted netlist. And this netlist includes all those unwanted R and C components we've been talking about, totally ready for post-layout simulation.
Now, a really critical concept to grasp here, especially if you're prepping for interviews, is the rule deck. A rule deck contains hyper-specific Foundry models. It essentially tells the extraction tool exactly how to interpret your layout based on the Foundry's actual manufacturing realities. Because these models are so incredibly specific, accounting for precise layer dimensions and exact sheet resistances, you absolutely cannot take a rule deck from, say, a TSMC 28nm process and use it for a totally different technology node. It literally just won't work. And look, you obviously aren't going to be doing this math by hand. In standard industry flows, we let heavy-hitting software tools do all the heavy lifting. The big names you'll encounter all the time are Cadence Quantus, Synopsys Star RC, and Siemens Calibre Exact or XRC. The exact tool you end up using just depends on the Foundry-qualified methodology your specific company prefers, but at the end of the day, they all serve the exact same vital function. Let's dive into Section 4, Analog Layout Techniques and Impacts. We'll focus in on how to actually handle these issues in practice. If you're relatively new to the field, you might be wondering, hey, if my layout versus schematic or LVS verification says my circuit matches perfectly, why isn't my job done right then and there? Why can't I just ship the chip? Well, the answer really depends on what you're designing. For digital circuits, parasitics mostly mess with timing, power, and signal integrity. But for analog circuits, parasitics are vastly more destructive. As an analog layout engineer, you're fighting incredibly delicate battles over gain, bandwidth, matching, stability, phase margin, and power supply rejection ratio. All of those specifications are ridiculously sensitive to even the slightest shift in resistance or capacitance. And this is exactly why analog layout is considered an absolute art form. Just imagine a current mirror with two matched transistors. If you route them asymmetrically, different via resistances and coupling capacitances will completely ruin the match. And boom, you've got a massive offset voltage. To fight back, we rely on vital layout matching techniques like common centroid and interdigitation. Instead of just plopping transistor A next to transistor B, we break them up into fingers and cross-couple them in a checkerboard pattern, like A, B, B, A. This is genius because if there's a thermal gradient or a chemical etching variation across the silicon, both transistors experience the exact same average error, effectively canceling it out. We also surround them with dummy devices. These are sacrificial transistors slapped on the edges that literally never turn on. We add them just so our active inner devices see the exact identical optical and physical surroundings during the manufacturing lithography process. And of course, you meticulously ensure symmetric routing and equal path lengths, basically guaranteeing that the parasitic environment is perfectly cloned across those matched paths. But here is the absolutely crucial point. PEX does not magically fix your layout. PEX doesn't optimize a single thing for you. It simply uncovers the mess you made. If the extracted parasitics are too high, you might have to go back and increase a metal width, jump up to a higher metal layer, or completely redesign your routing symmetry. It forces the analog layout engineer into this highly iterative, manual process of physical improvement. You just keep tweaking and extracting until your post-layout simulation finally hits those performance goals. Which brings us to our final section, Section 5, DRC, LVS, and PX Explained. I like to think of the three pillars of verification like this. DRC, or Design Rule Check, asks the question, did you build it according to the legal manufacturing rules? LVS, or Layout versus Schematic, asks, did you build the correct intended circuit? But PEX asks the final, arguably most revealing question of them all, now that you've physically built it, what unwanted electrical effects did that physical layout introduce? So, if an interviewer puts you on the spot, and heads up, this is a very common, very important interview question, they're going to ask you, if LVS passes, do we really still need PEX? Your answer absolutely must be a resounding yes. Look, passing LVS only means you wired it correctly on paper. It literally just confirms connectivity. To give you an example, you could route a 10-amp power line using a wire thinner than a human hair. LVS is going to pass that with flying colors because technically, yes, the wire is connected from point A to point B, but PEX will extract massive resistance from that tiny wire, and your post-layout simulation will immediately reveal that your circuit is completely starving for voltage. So yes, a layout can absolutely pass LVS while simultaneously being totally ruined by performance-degrading parasitic resistance and capacitance. When they ask you to define it, memorize this exact phrasing. PEX converts physical layout effects into electrical parasitic elements so that the real post-layout behavior of the circuit can be simulated. Saying it this way proves you understand not just what the tool does on a surface level, but why it's fundamentally necessary for the entire simulation flow. Ultimately, PEX serves as the vital bridge connecting the perfect frictionless world of schematic theory to the harsh, messy reality of physical silicon. It is the absolute final truth teller before a chip is ever sent off to be manufactured. Which leaves us with this final thought to chew on for this explainer. If every single physical wire you draw fundamentally alters the electrical truth of a design, is your schematic ever actually complete before physics has its say? Thank you so much for joining us, and keep pushing those boundaries from the ideal to the real.